Good morning, friends. Today I am going to present you a project that is bike sharing demand prediction. Here we have used linear regression. The summary of this project: in urban environment, rental bikes serve as the vital component of public mobility, enhancing accessibility and reducing waiting time for commuters. However, ensuring a stable and adequate supply of rental bikes at all times. This is essential for optimizing user experience and urban mobility infrastructure. This project aims to address the challenge of predicting the demand of rental bikes on an hourly basis, enabling rental services providers to efficiently allocate resources and ensure a consistent supply of bikes to meet user needs by leveraging historical rental data alongside factors such as weather condition, day of the week, and time of the day. Predicting model will be developed to forecast the expect bike count for each hour. The predictive model generates through this analysis will provide valuable insights for rental bike operators, enabling them to anticipate fluctuations in demand and optimize bike distribution and maintain schedules accordingly. Ultimately, the project aims to enhance the availability and accessibility of rental bikes, contributing the improvement of urban mobility and commuter convenience. Here is the GitHub link. Next, the problem statement. In urban areas, rental bikes are convenient mode of transportation, but ensuring there are enough bikes available when people need them can be tricky. This project aims to predict how many bikes will be needed each hour by looking at factors like past bike uses and weather condition. We will develop models to forecast bike demand accurately. This will help rental bike companies manage their resource better, ensuring there are always enough bikes for riders, thus improving urban mobility. So let's begin. So here we import our important libraries, that is NumPy, Pandas, Matplotlib, Seaborn, Plotly.express, Spicy, Sklearn, etc. So first we load our dataset, that is DF. Here is the first view of our dataset. In our dataset, there are 8,760 rows and 14 columns. Here is the each column name, that is 14 column, that is date rented by count, hourly temperature, humidity, wind speed, visibility, dew point temperature, solar radiation, rainfall, snowfall, season, holiday, and functioning. These are the variables. So here we have seen that there is no any duplicate value available. There are some null values available. So here we impute min data. Here is a description of our variables. Means date, the date on which the data was recorded, rented bike counts, the number of bikes rented on the given day, hours, the hour of the day means 0 to 23 when data was recorded, temperature, the air temperature in degrees Celsius, humidity, the relative humidity as a percentage, wind speed in meter per second, visibility, the visibility of in decacentimeter, dew point temperature, the temperature at which air becomes saturated when moisture and dew forms measured in degrees Celsius. So solar radiation, the amount of solar radiation received per square meter measured in megajoules. Rainfall, the amount of rainfall in millimeters. Snowfall, the amount of snowfall in centimeter. Season, the season in which the data was recorded, that is summer, autumn, winter, and spring. Holiday indicates whether the day was a holiday or not a holiday. Functioning day indicates whether it was functioning day for bike rentals or not. So here we have done some data wrangling task to replace the null values with some values. So here we have impute mean value. So first part of our project is data visualization. So first we have done univariate analysis. Here you have the chart, the distribution of rental bike counts. So here the distribution is not uniformly. So to overcome this, uh, we have a square root the variable. Then the distribution is something like normal distribution. The next chart is a pie chart which shows a holiday, means 95.1% has holiday, no holiday, while 4.93% have holiday. This is the pie chart of functioning day. There is 96.6% days are functioning day, while 3.37% there is no any rental bike counts. So next, now here is the bivariate analysis. Here is the line chart of average rental bike counts and in time. So we see here the trend of average rented bike counts. So here we can see that in the hours 6 to 10, the rental bike counts in the morning at 6 to 10 hours, the rental bike counts is increases and then decreases. While in the evening at 3 p.m., the rental bike count demand is increases, and at 6 p.m., the rental bike counts is demand of bike counts is at peak and then decreases. The next chart is between total rented bike counts versus temperature. As temperature increases, the rental bike counts also increases, and at some extent at the 30 degrees centigrade, the total rented bike counts here starts decreasing. Next is the bar chart between functioning day and total rented bike counts. Here, when there is a functioning day, then the total rented bike counts is about 6 million. While there is no holiday, there is no bike counts. The next chart is a total rented bike count versus wind speed. When wind speed less than 3, the rental bike counts at demand is high. When the speed is wind speed is increases, the demand also decreases. Next is the box plot between some variables, that is solar radiation. There is some outliers present in the data, while dew point temperature there is no outliers present. In the wind speed there are some outliers present in this column, while humidity have no any outliers, and temperature column there is also having no outliers. Then the next chart is between a scatter plot between rainfall and rented bike counts. So here we can see that when there is no rainfall, then rented bike counts is at its then the rented bike counts is at maximum demand. While there is some rain occur, then the demand of rented bike count slightly decreases, and when there is heavily rainfall, then the demand of rented bike counts is very less. So here is the scatter plot between rented bike counts and snowfall. When there is no snowfall, then the demand of rented bike counts is maximum. When there is some snowfall, then the demand of rented bike counts slightly decreases, and when there is a highly snowfall, then there is few demands of rented bike counts. So here is the average rented bike counts, and in winter season, the demand of the rented bike counts is very less, while in summer, the Demand of rented bike counts is maximum, followed by autumn and spring. When there is no holiday, then the average by demand of bike counts is maximum, and there is a holiday, then there is also the demand of rented bike counts. So this is the correlation heap map between different variables. From this correlation matrix, we can some insights. Temperature, there is a positive correlation between temperature and the number of rented bike count. This means that as the temperature increases, the number of rented bike counts also increases. Wind speed, there is a weak positive correlation between wind speed and number of rented bike counts. This means that as the speed increases, the number of rented bike counts slightly increases. The visibility, there is a negative correlation between visibility and the number of rented bike counts. This means that as the visibility decreases, the number of rented bike counts slightly decreases. Rainfall, there is a weak positive correlation between rainfall and the number of rented bikes. This seems counterintuitive, but it is maybe because light rain encourages people to rent bike for short trips. So overall, we can say that the correlation matrix suggests that temperature is the most important factor affecting the number of rental bike counts. However, other weather variables such as humidity, wind speed, visibility, dew point temperature, solar radiation, rainfall, snowfall also may have some influence. The next part is the hypothesis testing. Based here we have assumed some hypothesis that the first hypothetical statement is there is a positive correlation between temperature and rented bike rentals. So null hypothesis, temperature, bike rentals. So here we have tested, and the coefficient means p-value becomes p-value here is 0. So we can conclude that reject the null hypothesis. There is a positive correlation between temperature and bike rentals. So we can say that the statistical test used to obtain p-value, the Pearson correlation coefficient test, the spicy.test Pearson function calculates the Pearson correlation coefficient between these two variables. So the hypothetical statement 2 here, the distribution of bike rental is different during different season. So here we perform the p-test, and here p-test also 0 and t-statics is 2095. So we can conclude that reject null hypothesis. The distribution of bike rental is different during different seasons. Next, the third hypothetical statement is the mean rented bike count is significantly different between functioning and non-functioning day. So after doing this test, the p-value about to 0 and t-statics is 19.49. So reject null hypothesis. This means rented bike count is significantly different between functioning day and non-functioning day. So next step, the feature engineering and data pre-processing. Here we have removed the outliers present in our data set. So here some outliers present in the wind column, some outliers present in the solar radiation, some outliers also present in the rainfall and snowfall. So we have removed this outliers. After cleaning data look like this. Next step is we have done categorical encoding on date column, season, holiday, and functioning day. So our data is look like this. And after doing this level encoding, we have select some important features. So here we have selected hours, temperature, humidity, wind speed, visibility, solar radiation, rainfall, snowfall, season, holiday, and functioning day as the feature of independent variable. So here we have transformed our data using min max scalar. Here we have scale our variable, that is xdf feature scale scalar dot transform xdf. Mm, Then here is our data set independent variable. These are the independent variable. Next step, we have split our data into 80:20 ratio. 80% are trained data and 20% are our test data. So here we can see that 56,008 rows are our trained data and 1403 is our test data. So here first model is linear logistic regression. No. First model is linear regression. Here we have found out the array predicted value of our independent variable. So here is the dot point shows our uh, actual data points, and this red line shows the linear regression line. So from this, here MSE value is 49, root mean square value is 7, R square score is 0.67, adjusted R square is 0.6. So from this model, the MSE value means loss function are very high, and adjusted R square also about 0.6, which is near 0.5. So we cannot prefer this model to implement this. So we use next model. So here we have used lasso and risk to minimize our loss function, but there is no any improved. This function cannot improve our model. So next we use decision tree to minimize our loss function, but MSE comes here also 25, adjusted R square is 0.8. It's our loss function improve, but we should improve our model efficiency. So we have use here random forest to minimize our loss function. After doing this test, our MSE becomes 2.269, which is very good for our model, and adjusted R square becomes 0.85, which is near 1. So from this, we can say that random forest is an assembling learning method building multiple decision tree. During training, the outputs mean prediction, the individual regression allow them. MSC is 2.29, measuring the average square difference between predicted and actual value. Lower is better. Similarly, RSME, lower is better. R square coefficient, that is closer to 1, is better, and R adjusted R square, which is closer to 1, means it is also better. So here we have used random forest with grid search to optimize our hyperpara optimization, to optimize our hyperparameter. So here we have used after doing this model, here are the value that our MSC is 21 and adjusted R square is 0.86. So here is not any improvement in this model. So MSC increased significantly this to this after applying grid search. This indicates worse performance in terms of prediction error. So We have used next model, that is XGBoost. After doing this, our MSC is 3.75 and adjusted R square is 9.75. So our model improved here. So measure XGBoost is a powerful machine algorithm based on the gradient boosting. It's designed for speed and performance. MSC, the measure of average square difference between actual and predicted, a lower MSC 3.75 indicates good model performance with fewer errors. And adjusted R square is very closer to 1. So next we have cross validation and hyperparameter tuning. We have used XGBoost with randomized search cross validation. After doing this, our root mean square error comes 4.89, root mean square error comes 2.21, adjusted R square is 0.890. So from this we can conclude that there is an improvement in the training set metrics after applying randomized search CV, indicating that performance has increased. However, the primary goal is randomized search CV is to enhance the model generalization to unseen data. This test metrics demonstrate that the model performs reasonably well on new data, suggesting that generalization is better than initial model, which was evaluated slowly. Training set metrics. So here we have done some future work. So from the above models, we can conclude some points here. That I have performed linear regression, decision tree, random forest with grid search, cross validation, XGBoost and XGBoost with grid search, cross validation to minimize loss function and improve our machine model. Random forest ML model, the MSC is 2.29, RMSC is 4.8. Overall, these metrics suggest that the model performs exceptionally well in predicting the target variable. Random forest with grid search, CV, the MSC is 20.75, RMSC is 4.55, R square is 0.8667, and adjusted R square is 8.0.667. This model does not perform well on training dataset. XGBoost model of machine learning, the MSC is 3.3785, RMSC is 1.9. These metrics suggest that XGBoost model also performed well on predicting the target variable. XGBoost with randomized search cross-validation model of machine learning. The MSC is 4.89, RMSC is 2.21, R square is 0.9685, and adjusted R square is 0.9683. This model also performed well on training data. So from this table, we can conclude some points. During regression, these points from EDA, most number of bikes were rented is summer season, followed by autumn, then spring, winter being the last. Maximum number of bikes were rented on non-holidays. June is the month on which the most number of bikes were rented, followed by July and May. According to a data, the most number of bikes were rented on 18 p.m. means evening 6 p.m. People preferred a ride of bike when temperature between 19 to 25. And from machine learning part, we can conclude some points. Best performing model. The standard random forest model shows the best performance based on MSC RMSC, suggesting it the highest predictive accuracy. Model with variance explanation, the XGBoost and randomized search CV has the highest R square and adjusted R square, indicating it explains the most variance in the target variable. Grid search CV impact. Applying grid search CV to the random forest model did not improve performance and in fact result in worse metrics. This could be due to overfitting or suboptimal parameter tuning. XGBoost model. Both standard XGBoost and XGBoost with randomized search CV perform well, but a standard XGBoost has a lower MSC and RSC, indicating better accuracy on this matrix. So that is all about my project. Thank you very much.